We are looking at the function given here and trying to use the techniques we've learned in this course to draw an accurate picture of the graph of this function. In the first 4 steps of our procedure, we've talked about information that comes directly from the function. So continuity, domain, intercepts, end behavior, that sort of thing. Here we're going to move on to information that we get from the derivatives of this function. So the thing that we need here is to calculate the derivative of this expression. By this point of the course, we should be comfortable in doing so. If we were to use the product rule and do some simplification, what we are going to end up with is the following expression. Now, it is vitally important that you factor this expression as far as you possibly can. So you can pause the video at some point here and make sure that you can get to this result at the end of the day here. Negative 5/3 times x plus 1 over x to the 1/3. Now we are going to build a sine table for f prime. The reason we want to factor it is because it makes our life very easy when we construct this table. We can easily see that the derivative is equal to 0 when x is negative 1, and we can see that the derivative does not exist when x is 0. Both of these are critical numbers. A critical number is a point in the domain of the function, so it has to be an actual point on the graph of your function where either the derivative is 0 or the derivative does not exist. And we have done the work and factored this thing to be able to build a sine table. So a sine table is essentially taking a number line, listing the critical numbers there, and you're taking the number line and dividing it up into different segments. So you list the factors of the derivative on the other side there. And then you try to determine the individual sign of each factor and multiply them together to get the overall sign of the derivative. By the mean value theorem, that'll tell you where your function goes up or down. Now, 5/3 is always negative. In each of these 3 regions, it will always be a negative number. X plus 1 is a linear factor. It changes its sign at x equals negative 1. So when you are a number less than negative 1, like negative 1 billion, this is a negative. But as soon as you cross and you go over and you're greater, this thing becomes a positive. X to the 1/3 is the cube root of x. It changes its sign with x. So if x is a negative number, it's a negative number. If x is a positive, it's a positive. The derivative is the product, the sign of the derivative is the product of all of these signs. So at the end of the day, we'll get a negative, a positive, and a negative. What does this tell us? That if the derivative is negative, that means the function is decreasing on those intervals. So here the function is decreasing from negative infinity to negative 1 with a round bracket, and round bracket 0 to infinity. And our function is increasing only on the interval negative 1 to 0. The definition of increase and decrease that we use says it has to be strict inequalities here. We don't allow it to be equal to 0. And that means we have to use round brackets at each of those critical points. The next thing we'll do is talk about minima and maxima. According to the above, we've got all the ingredients for the first derivative test. So what we do is we take the first derivative and we look for spots where it changes its sign. So here the function is going down and there it's going up. So it looks like we've got a local minimum at x equals negative 1. In the other instance, we've got a function that's going up and then down. Here we've got a local maximum at x equals 0. Now, I know that these are actual points because the domain of this function is all real numbers, and so each of these values does get represented by a dot on this screen, on the graph, sorry. Now, in the first instance, this is going to be some kind of bump because f prime of negative 1 was 0. So that means we're going to have some kind of flat bit, whereas in this situation here, we are going to have some sort of corner or cusp, some sort of pokey thing, because f prime of 0 does not exist. There has to be something on the graph there. It's just that the derivative does not exist. So those two steps give us information about the derivative, and that means it tells us something about increase and decrease. Where we want to go next is that we want to go to the value. We want to talk about the second derivative. So at this point, what we want to do is talk about concavity. F prime of x was given by this expression. You could write it as a product. However you want, you should have more than enough ability to go through and take the derivative of this. If you were to take the derivative of this and then do the work to factor it, you will end up with the following result. So it's a similar looking expression, but obviously different. Now, the reason we like this is because it's very easy to see where the second derivative is 0. This happens when x is 1/2. And we can see that the second derivative does not exist once again at x equals 0. That non-existence persists from the first derivative onto the second. If the first derivative does not exist, it isn't possible for the second derivative to exist. So that's why you should see that similar sort of behavior. Now we are going to build a sine table for the second derivative in the same way that we did for the first derivative. So we'll put in those special points in increasing order, 0 and 1/2, and then we'll list the factors of the second derivative. We'll split the number line up, and then we'll fill in the signs. So just like before, this -5/9 is negative everywhere. 2x minus 1 changes its sign at 1/2. So it's going to be negative when you're below, and it's going to be positive when you're above. X to the 4/3, because of that fourth power, it will always be a positive. At the end of the day, the second derivative is positive there, and negative there. So the function is concave up from -infinity to 0 with the round bracket, and 0 to 1/2 with a round bracket. It's concave down from 1/2 to infinity. And then the final thing that we are going to look for is just an easy result that comes about from our table here. Inflection points. These are points in the domain of f where the second derivative changes sign. It's not just a point where the second derivative is 0. It's not just a point where the second derivative doesn't exist. Those are necessary but not sufficient. You need to look for a sign change in the second derivative. And I'm hoping that you can see from your table there's only one inflection point when x is 1/2, because that's where the function changes its concavity from up to down. So now what we've got is a big list of information, and it can be overwhelming, right? You have to put it all together. And this takes a little bit of time, and it takes a little bit of work, but it's an important step. So keep track of all your work, write everything down, and be clear about what it is that you're doing. So we're going to make a number line. We're going to try to do this in a reasonable fashion, and then just start collecting the information that we had. Okay? If you look back at all of the steps and you try to follow them in order, our function was continuous everywhere, so there are going to be no breaks. We had axis intercepts. We had one axis intercept at the origin and the other one at -5/2, so right there. We had no symmetry to speak of, And our end behavior was that our function started up and it ended down. So somewhere as we go from left to right, we will have to fall. Now the next thing comes from talking about the first derivative. So this is where underneath you can label whether your function is increasing or decreasing. So what we had found is that we were decreasing until -1. We were increasing from -1 to 0. And then we were decreasing again after that. So we were falling. And then we'll list our concavity. So we were concave up until the origin, concave up again afterward, just until the point 1/2, and then we were concave down after that. Now, the minima and maxima occur as well. And so we discovered that we had a local minimum when we are at -1. And so it turns out that if you plug this into the original function, this will be at the height of -3/2. So roughly here, there's a local min. The max was at the origin. We already know this. The inflection point happens when we are at f of 1/2. And so if you were to take f of 1/2 and plug it into a calculator or just try to evaluate it, you get about -1.88. And that happened when we were at 1/2, so it's somewhere around there. So now we put it all together. We are starting up at positive infinity. We have to have a function that is falling but smiling. And it falls but smiles until it gets to this minimum. Oh, and sorry, I put the minimum slightly in the wrong spot. It should be right about here. So we just draw something in, kind of like this. It's a horrible picture. So let me try again. There we go. So we go through that route, and we have to hit that minimum. Now, remember that at f of -1, we have a bump for our first derivative being 0. So this is going to be a round spot down there. Next, what has to happen is we have to increase but smile. We have to, here we're concave up. We have to continue being concave up and rise to that local maximum. At that local maximum, we have a cusp or a corner. What that means is we switch, our derivative does not exist, and it becomes infinite on one side and a different sign of infinity on the other because we're going from up to down. So we'll have a sharp, pokey thing right there, and then we'll have a decreasing sharp, pokey thing. So we're concave up but falling until we hit this inflection point. So we'll be falling there. So in all of these situations, we are concave up. And then the next thing that happens is we have to continue to fall and be concave down. And then just drop that way until infinity. And right there, we've put all of this information to get us a very good picture. Yes, you can use technology to graph this, and it's very quick. But technology becomes a black box, and you then don't know what it's doing or how it's getting it. Using things in this way gets you all of the important information. You know exactly what it's doing, where it's doing it, and it's a very valuable